Hello, my name is Laura Chen from the University of Toronto, and I'm here to present to you disambiguation techniques for freehand object manipulations in virtual reality. This work was done in collaboration with Professor Ravan Balakrishnan and Professor Toby Grossman. First, let me talk to you about freehand interactions. So freehand interactions is a way for users to interact with virtual objects using their bare hands, similar to how they would interact with real-world objects. And the virtual object would have physically realistic reactions to the interaction. The concept of freehand interactions is especially promising for virtual and augmented reality because it feels natural and familiar to users, since we all have a lot of experience already with interacting with objects in our daily lives. And so we can rely more on our instincts and previous experiences instead of arbitrary commands or gestures when we are touching, holding, and playing with virtual objects. But one significant problem for freehand interactions is dealing with the ambiguity in the resulting outcome of the interaction. In real life, a lot of times one single gesture can mean a lot of things, and one action with your hands can be used to do different types of tasks. Here, these pictures all show a polling gesture, but they're meant to do different things under different circumstances. And this is similar in VR and AR. You can use the same gesture to activate different operations on a virtual object, depending on the context, the object's properties, and the user's intentions with the object. So let's say we're in a shape modeling application and we see a globe like this. If we wanted to do something with this globe, maybe flatten it or stretch it, our first natural reaction would be to grab the globe and play around with it to see what would happen. If we use our hands to pull on the globe, should this globe be stretched, like seen here, or maybe it should be scaled, or maybe open itself up? The action is the same. In all three cases, we're pulling on the globe, but the resulting effect on the globe is different. And this is what we call operation ambiguity. Operation ambiguity from gestures is commonly seen in user-elicited gesture studies. So for example, in a work called Magical Hands, the authors developed a system that uses user-elicited hand gestures to make animations in VR. We can see here on the right that one participant is using the motion of her hands to make a tornado animation and kind of turning her hand to indicate that the tornado should bend itself. For these user-elicited gestures, sometimes the participants would use the same gestures to indicate different effects. So how do we resolve operation ambiguity then? Well, one straightforward way is to just map each gesture to a unique operation. But this method takes the naturalness away from gestural interactions, since the users are forced to remember an arbitrary set of commands to invoke operations on a virtual object. And if the application is complex, then it would be hard to remember such a large set of commands. A cheat sheet that lists all the available commands would work, but it's cumbersome and it's hard to find which gesture command mapping you're looking for. So we wanted to find a way to resolve the ambiguity while still keeping the benefits of freehand interactions. We thought about what factors are important to consider when resolving the ambiguity. First of all, when the user is freely interacting with virtual objects, their hands are mostly already occupied with the object, and it would be hard to use hands to maybe task switch between interacting with the object and disambiguating the operations. So we considered other input modalities that could be used for disambiguation. We focused on three modalities, which are gaze, speech, and foot tap. Also, it's not clear when these ambiguity resolutions should happen. Initially, we thought that it made sense to resolve the ambiguity when the user is in the middle of performing a gesture on an object, so we thought to provide other options for the user to choose from during the interaction. But after looking at some related works, it seemed that providing these alternative options before the user begins their interaction, or maybe after they have completed their interaction, were also plausible designs that we could consider. So we tested out 3 different timings at which the ambiguity is to be resolved. Some of the previous works that influenced our design considerations are previews, feed-forward and feedback mechanisms, and suggestive interfaces. Previews let users get a sense of what is the effect of applying a command before the command is actually called. Feed-forward and feedback mechanisms usually give immediate and continuous feedback during an operation to show what has already been done and what's to follow. And suggestive interfaces first let the user give hints to the system about what the user wants to do, and then suggest possible operations that the user can select from. There are also other works on resolving input ambiguity in other areas of research, like desktop interfaces. But the ambiguity that our work tried to address is in the intended outcome of performing identical gestures. Okay, so let's talk about the system and the disambiguation techniques. We developed our system in a VR environment which supports freehand interactions with 3D virtual objects. We used an Oculus Rift as the VR head-mounted display, and we attached a leap motion sensor at the center of the headset for hand tracking. And the application is ran on a Windows 10 machine. In order to show that, to show what options are available to the user in the disambiguation process, we use a disambiguation menu which shows 3 preview cubes. And when the user's interaction with the object is ambiguous, this pop-up menu would appear above and at a distance from the object so that the user can choose the operation that they intended. As I mentioned earlier, we explored 3 modalities that can be used to select the intended operation, which are gaze, speech, and foot tap. For gaze, we used head gaze instead of eye gaze. In head gaze-based disambiguation, a circular cursor follows the user's head direction. And if the cursor falls on one of the preview cubes and stays on the cube for more than 0.5 seconds, then that operation is selected. Speech selection works just like how you would expect it to work. We place the associated speech command above each preview cube, and the user can select an option by speaking the command out loud. And for the foot tap modality, the ground in front of the user is divided into 3 rectangular selection areas that correspond to the 3 preview cubes. When the user's foot hovers over an area, then the corresponding cube is highlighted in green, and tapping the foot on that area would select the cube. Apart from modality, the other factor that we explored is the timing at which the disambiguation menu appeared, which are before interacting with the object, during interaction, or after the interaction. In the before condition, the menu is shown when the user's hands are hovering near the object, but before pulling on the object. The cubes show a static preview of the operations, and the user can select an option before interaction begins. And once it begins, the menu becomes hidden. And for the during condition, the menu is shown after the user has begun pulling on the object. While the user is interacting, the preview cubes are continuously updated in real time to show the user what is the effect of doing the same action on other options, and the user can smoothly switch between those options. In the after condition, the menu becomes available after the user has interacted with the object and released it. And the menu shows the static results of alternative operations that the user can choose from. We conducted a study where we evaluated the performance of all the combinations of modality and timing. But in a pilot study, we also found that apart from modality and timing, operation distinguishability could be another important factor that influences the performance. So in the formal experiment, we included 2 sets of operation alternatives. In the high distinguishability set, the operations were highly distinct from each other, and in the low distinguishability set, all the operations looked very similar to each other. And we hypothesized that selection might be more difficult when the operations looked similar. We recruited 12 participants to do an object shape matching task. In each of the trials, a semi-transparent shape is shown, and that shape is the result of applying one of the possible operations on the globe. The user needs to push or pull on the globe and select the correct operation until it matches the transparent shape. From the results, we see that head gaze had the lowest task completion time, closely followed by speech, and foot tap had the highest task completion time. But most participants reported that they preferred head gaze. In terms of timing, the during condition was significantly faster for completing the task, followed by the after condition and followed by the before condition. For distinguishability, as you might have expected, high distinguishability operations were faster to complete than low distinguishability operations. What we found interesting was that there was a significant interaction effect between timing and distinguishability. And so for high distinguishability operations, the task completion time was similar across all the timings, as we see here, where the orange bars all level around about 6 seconds. But for the low distinguishability operations, the before condition had a much higher task completion time than during and after. And why is this? Well, the participants explained that for low distinguishability operations, it was harder to judge which operations they should choose until they actually started doing the gesture. We also collected a raw NASA task load index questionnaire focusing on modality, which gives us a sense of the perceived workload that each modality imposed when doing the object matching task. So taller bars here indicate more workload. And we can see that overall, gaze and speech had similar workloads, but foot had comparably more workload than the other modalities, especially in terms of physical effort and frustration. We also collected several other metrics like selection error and manipulation error counts and the user's subjective ratings and feedbacks. You can find more details about those in the paper. From the results, we found that the during timing was especially useful for low distinguishability tasks because it was hard to tell which option is the desired operation until the user is already in the middle of interacting with the object. On the other hand, for high distinguishability tasks, the user can easily tell which operation was the correct one even before starting the task. So although the during timing is preferred by participants, the before timing is also a feasible design to consider for high distinguishability tasks. Scalability is also important to consider for future work. In this paper, we experimented only with a single gesture on a single virtual object, but in a real application, the user's actions could be part of a large workflow and ambiguity could occur at any point in that workflow. Also, we give participants only 3 operation alternatives to choose from, but the number of alternatives could also have an effect on the performance. Our study, of course, had some limitations. The sample size of 12 is relatively small for a 3-factor experiment, and we tested on a limited scenario where the participants only interacted with a single object. So for future work, it would be important to understand how our results can generalize to resolving ambiguity when multiple objects are present. To summarize, we presented a system and a set of conditions for disambiguating freehand object interactions in VR. We conducted an analysis of the effect that modality, timing, and distinguishability have on the performance time and error. And we found that overall, the head gaze modality and the during condition achieved the best performance and were the most preferred by participants. Thank you for listening.